So before that, I'll just talk a little bit about some approaches that can help you be better at linear algebra. So throughout this notebook, I'm gonna share with you a link from a YouTube channel called 3 Blue, 1 Brown, or the other way around, 3 Brown, 1 Blue. So it's a very, very good video channel in the sense that it tries to visualize a lot of these concepts. And usually one problem that everyone has is that since we're talking about linear algebra and high dimensions, it's very hard to visualize the stuff in high dimensions. And I mean, the board, we can probably do a very good 2D visualization, but for high dimension, it's more problematic. So it's really good to kind of have some geometric intuition about the things that we're discussing. So really one of the kind of resources that we're recommending for this course, for the linear algebra part, is just a YouTube channel, really. So if you have free time, if you, I don't know, like if you like me, eating your dinner while watching TV, so you can probably try that out. So I'll just search for it here, 3 brown, 1 blue, yeah. And if you're also interested in more advanced topics like how ChatGPT works, how things like that work, it's a very useful topic. So like, for example, here, they're really talking about a lot of concepts that we'll cover and touch on. So if you feel you're not super comfortable with a lot of material or you need more intuition, I really recommend this channel essentially. Okay, so, and the other thing about the whole course is that machine learning is essentially glorified high-dimensional probability. So what you really need to focus on and what you really need to know to get a very good grade is linear algebra and probability. So if you ever taken an advanced linear algebra course, you will see a lot of similarities to like a machine learning course. So be very kind of careful with that unfortunately there is no escape from it. You cannot really understand the course well if you don't have a good understanding of basics of linear algebra. You really need to be very comfortable with working with them, both in the application, the coding part, and also in theory, in the proofs that we will talk about. So the approach that we've taken today is, instead of, again, going over the slides, I'll talk a little bit more in terms of the coding and the application, and we'll go over some of the key concepts that you really need to know for the course. And again, just like the probability part, we have, so let me actually go to the website and show you. So in the schedule part, so all of the material are shared. First of all, the linear algebra notebook, if you want to kind of have access to it and just follow it live, you can have access to it. And the slides are shared in the probability part. But we also put a probability review from Stanford. It's a very short document, like 13 pages. And we also have this linear algebra review, which is like longer. But again, if you found yourself alien toward a lot of these concepts, make sure to go over it, especially during these few holidays, because then you will see the course just keeps on going and you'll see a lot of these piling up. So this is my kind of honest suggestion that if you feel uncomfortable with it, just go over it and they won't take you a lot of time, especially if you already have taken a course before. Okay, so let's start this. And again, you can have access to the notebook. Let's first kind of have some common understanding. For this session and this course, we're assuming you've heard about a vector, a matrix, some basic vector operation like addition of two vector, how it works, or multiplication of matrices, although we will go over it, that's like class specific one. So we're assuming you kind of know how basic linear algebra is working with the like addition and subtraction and the scalar multiplication. And then we'll build on top of that. So the first thing we will talk about is the difference between like kind of the wording difference. Like what is a scalar, what is a vector, what is a matrix? So whenever you heard about a vector, we usually need an n by 1 matrix that looks like this. So this is a vector for us, x, and it's an n by 1. It can have values and different dimensionality. So this is a vector. A matrix is essentially, you can think about it as a bunch of vectors concatenated to each other. So that's going to be a two-dimensional object. So this is a one-dimensional object because all you have is just a bunch of like n different values. And then you can represent them like this. For a matrix, we have a two-dimensional like object or two-dimensional tensor, which we'll talk about. And a scalar, just a number that we usually work with in like vanilla algebra, like 2, 3. We can think about this as actually being a 1-by-1 matrix. Okay. And the idea is that we already know some operations on the scalars, on the numbers. We want to see how they will change when we are kind of generalizing it to higher dimensions, like to vectors, to matrices. So for example, addition is going to stay almost the same. So you're just adding elements wise, but multiplication will change. We'll see. And finally, if we have an object or like a matrix that is higher than 2-dimensional, so like 3-dimensional. So like, for example, a matrix is a 2-by-2 matrix. And if you stack these matrices on top of each other, now you have a 3-dimensional object. And we call that a tensor. So anything higher than 3, we also call that a tensor. We don't make different names for different ends. So 0-dimensional tensor is a scalar, 1-dimensional is a vector, 2-dimensional is a matrix, and finally 3 and above is a tensor. So for the first half of the course, we're going to work with a library called NumPy, which is short for numerical Python. And it really helps us to do a lot of nice things in linear algebra. Later, we'll learn about another library called PyTorch, which is specifically designed and kind of sped up for working better with matrices. But for the first half of the course, you only need to use NumPy. And one thing before I forget, your first assignment will be released, I think, after the holidays. And you can only use NumPy for that one. So a lot of things that we ask you to implement in the assignment, they have already been implemented in different libraries because they're basics of machine learning. But what we want you to do is to really learn how things are working under the hood. So our assumption is that you only need to know NumPy. So, and that also could be a good news for those of you who doesn't have a lot of background in Python or like machine learning with Python, because really all you need to do is know NumPy. So let's just start. So first thing you do, so I'm working here on Google Colab. If you don't have a powerful machine, you can work on Google Colab, or if you have any kind of system like Conda or anything installed in your computer, you can just use that one. There is no limitation in that term. So first thing I do is I import a bunch of libraries that I'm going to use. So a lot of the functionalities that we are using is in the main NumPy kind of library. And a lot of them are going to be in the subcategory of LINA-LG. So it's essentially a bunch of functions that are for linear algebra inside the NumPy. So one function that I specifically need for today is a function called EIG. So I'm just going to import it. It's going to be for later. It's representing the eigenvalue. And finally, I'm just need another function for the norms. Unfortunately, I don't use the NumPy one because I want to use different orders of the norm. So I use from scipy.stats. And one thing just before going on for the coding, you will see like I'm doing something like matrix multiplication using a function like NumPy dots. There are usually more than one way or more than one function to achieve the same functionality. As long as they are the same thing, you can use them. So don't be afraid if you're using like one function, I'm using something else. As long as our results are the same, it's great. Usually we have different libraries, and these different libraries, they implement their own type of function. And sometimes even like in the case of matrix multiplication, we're going to talk about this, there are some very small nuances of how two different functions kind of find or like calculate the matrix multiplication, for example, which is, again, in most cases shouldn't be that different. So let's start by creating our first row vector, which is essentially a 3-by-1 vector, and we have 5, 7, 9. So to do that, you can just use np.array. So numpy.array or np.array essentially tells your Python interpreter that, hey, we're working with an array, and essentially it's a vector. So like one thing I'm going to do is I'm going to print also the shape of it. So you see, this is the vector that I'm having, and the shape is 1/3. So if I had it like this, so if I remove the first brackets, which might look redundant, you see the shape would change to just 3. And one thing to remember from now for your assignments is that your assignments will be auto-graded. So essentially your code will give an output, and then the autograder will test that output versus its expected output. One thing that can happen is that sometimes your code outputs this 579, but then you will get something called the mismatch error. And then it says, oh, I expected a 3x1 object. You will be frustrated because your answer is correct. So all you needed to do is just to change the shape. Sometimes it's the other way around as well. So your code might give you something like this, but the autograder expects just like a 3 vector, like not a 3x1 vector. So that's just one thing to keep in mind, especially when you're doing your first few assignments, like assignment 1 and 2. That is mostly you doing a lot of functionalities. So be very careful with the dimensions and know that they are different. So a 3x1 vector a 1x3 vector that I just showed here is different from just like a vector of size 3. Make sense? Okay, so now let's define it really as a vector, which is a column vector. And we sometimes use this. So usually, like by definition, a vector is a column vector. So it's an n×1 matrix. But we can also have a row vector. So like 1, 2, 3, 4, 5. Essentially, they're the transpose of each other. And we'll talk about what is a transpose. So to define an actual vector, so what I'm going to do is something like this. So I can just take the vector that I had and I can transpose it. And now I should have a 3x1 vector. And another way I could do it is to literally like define it like this. So you see, I define it as like brackets. Like the first bracket is the first row, which is like 5. And the second bracket is the second row, which is 7. And the third bracket, which is 9. That's also one other way. So the way we're representing things in NumPy, if you haven't worked with it a lot, can be a little bit confusing at first, especially for the matrices, because you see these kind of nested lists inside each other. But just take some time, use some of these functionalities. I highly recommend you, especially if you are a beginner at coding with Python, always try to print out the shapes, because that will give you a very nice flow of, okay, what things I'm doing. So you will definitely at some point of your assignment 1 get a mismatch error from either one of the functionalities or from the autograder. So be very careful with the shapes. Always try to track them. It's a very nice step for the debugging. Okay, so now that we defined our like vectors, now let's go into matrices. So now let's define a matrix. And again, as I said, to define it, essentially each of these kind of inner elements, they are defining a row for you. So that's essentially this way that I put it is very nice because you can really see how this is a matrix. But I could also remove these spaces without any issue. And it would be essentially the same exact thing. So you see, this way it's a little bit harder to visualize, but the previous way that we had it was much easier. So this is the matrix that I have. And by the way, if you want to find the shape of a NumPy array, all you need to do is just to call dot shape. Okay, call dot shape, no parentheses, it will give you the shape. And it will make a distinction between a 3x1, for example, vector and a vector of size 3. Now let's define another matrix, matrix B, and let's have some fun with them. So let's see what's going to happen if I multiply my matrix by a scalar. So the matrix A is essentially a 3x3 matrix of all ones. And again, some of you who are more advanced might ask me, could I use another function like numpy.ones to build that matrix? Yes, that would also give you the same exact results. Now, if I multiply that matrix by a scalar, by definition of a scalar multiplication, all of the elements will be multiplied by the scalar. So I'll get, again, a 3x3 matrix of all 5s this time. If I add 2 matrices, again, super easy. You just add them element-wise. So this is the formal definition, which is usually kind of harder to understand. It's like you can really see it. If you add, for example, this matrix of all 5s, sorry, the first matrix, yeah. The matrix of 1, 1, 1 to this new matrix, which is 2, 4, 6 that is repeated 3 times, you'll get something like this. Where is it? Yeah, you'll get something like this. So you're essentially adding everything element-wise. So hopefully everything is good so far. Now let's get into the transpose. So transpose is one of those very, very important operations. So when you're transposing a matrix, what you're doing is you're essentially changing the rows and columns. So again, if you think about this as being like the row, you're kind of flipping it 90 degrees, and that will give you the transpose. In Python, you can easily find the transpose by calling dot A. There was dot shape. By calling dot T, you can easily find the transpose of the matrix. You can also use numpy dot transpose to do that, but usually this is easier and this is nicer to see as well. So just to give you an example, the first matrix that I have, again, see the shape, it's a 3x4 matrix. If you want to transpose something and see if it's correct, one way to do that is literally go over and check all the single values. But if you have, I don't know, like a 200x20 matrix, you cannot really do that. So the best thing to do here is just to work with the shapes. So if I change the rows and columns, I kind of expect that the rows and columns have actually flipped and changed. So instead of a 3x4 matrix, I'll get a 4x3 matrix. Okay, now let's go to matrix multiplication. Just a quick question. How many of you have never done matrix multiplication before? Don't be shy. Okay, good, pretty good. Hopefully you know how matrix multiplication works. I don't know, like high school or basic math. So essentially what you're doing is if you're multiplying A and B, you are multiplying the rows from the first matrix A in the columns of the second matrix B. So for example, if you multiply the first row with the first column, in the new matrix, you find the element located at 1, 1. So row 1, column 1. Again, if you want to do it backwards, so if you want to find the element that is located here, so this is row 2, column 1. What you need to be doing is you need to go to the first matrix, take the second row, multiply it in the first column of the second matrix. And this is how it generally works. And this is very nice because again, if I want to have access to, let's say, just one value here, which is just this 2 and 1, for example, x of 2 and 1. I don't need to find this whole thing. All I need to do is just to find a row and a column and then multiply them together. So my computational cost is significantly reduced here. We're not going to touch a little bit, we're not going to touch a lot on like the computational costs in this course. But if you're interested, or if you're interested in, I don't know, like doing your own project or creating your own startup, it's probably something very important. And one of the ways that we can really save a lot of computation is using this simple trick that to find an element in the multiplication, you don't need to do the whole multiplication. All you need to do is just to trace back, okay, which row and which column I needed. And that would significantly reduce the amount of computation you need. So to multiply them, obviously, Python has functions for it. So one function that we used here is called numpy dot, which is like np dot dot. There are multiple functions. So you can either use numpy dots and you get this matrix. Just to show you that there are different ways to do it, you can also use something like this, matrix A, @ matrix B, and hopefully it works. You see this @ is kind of reserved in Python for matrix multiplication. That's also another way to do it. Or you can even use a function called numpy np.matmul, or matrix multiplication, between matrix A and matrix B. And all of them will give you the same exact results. There are some nuances. So for example, np dot, we will talk about dot product. Hopefully you know it by now. But what it does is that it's essentially defined to find the dot product of two vectors. So if you had two vectors of size, let's say 3x1 and 3x1. So one important thing in matrix multiplication, as you know, is that the dimensions should match. So you can multiply a matrix that is 5x6 only in matrices that have 6 as their number of basically rows. 6 by, for example, 10. So these values should match with each other. But if you try to multiply a 3x1 vector, let's call it B, and let's call this one U, this will give you an error. It will tell you, hey, the dimensions are not matching because this is 1, this is 3. But usually when we're multiplying two vectors, we usually need U transpose V, or the dot product, which is essentially you have something, and write it here. So the dot product is something like this. So you have V1, V2, V3. This is your matrix. This is your vector V, and this is your vector U, U1, U2, U3. So essentially, what you want to do when you do the dot product between U and V is something like this. It's U1 V1 plus U2 V2 plus V3. Or you can write this as V transpose, okay, times U. Because V transpose U is something like this. V1, V2, V3 times U is U1, U2, U3. And if you do this multiplication, it's a valid matrix multiplication. So the difference is if you have this numpy dot and if you have a vector, it automatically understands that, oh, you mean the dot product for the vectors. So if you have vectors, it finds the dot product. If you have matrices, it does the regular matrix multiplication. That's why we used it here. Any questions? And again, you see there are like 3 different ways to give you the same exact result. So now let's see another example. So let's say we have these matrices. So both of them are 3 by 2, but you cannot multiply 3 by 2 matrices because again, the number of columns of the first matrix should match the number of rows of the second matrix. And that's why you get a very different sort of multiplication from the number multiplication. Because in numbers, it doesn't matter. If you multiply A with B, is equal to B times A. But in matrices, A times B is up for the numbers. But A times B is not equal to B times A. In fact, if you don't have a square matrices, if you can find A times B, you're guaranteed that you cannot find B times A. Because again, if you don't have a square matrices, number of rows and columns are different. If they're matching in A and B, they're definitely not going to match in B and A. So this, you will get an error which says, like this is the error that we kind of created here with the try and except, but you essentially say something like, oh, error in this line or error in this thing. Usually it's your mismatch. So always track the shapes, okay? And finally, for the like matrix vector multiplication, it's something very kind of interesting and very useful. So again, if you just follow the dimensions, that look very easy. So you have a 4 by 3 matrix and you're multiplying it in a 3 by 1 vector. What is going to be the output? The output will be a vector, which is now size 4 by 1. So we use this a lot for solving equations. So essentially, when you're solving equations, you also do something like this. You have a bunch of unknowns, and you want to find like how you can kind of tweak these unknowns, how you can find some values for these unknowns to satisfy a bunch of equations. So essentially, this is where this thing comes into play. And finally, just to give you some useful functionalities, you can just define some random matrices, random functions using random.rand. So essentially numpy.random gives you different randoms. This is very important, especially if you want to initialize an algorithm. So we need to usually start from a random point, which is usually not 0. So a very good question is, okay, how can I kind of build this such matrix? The answer to that is you can easily use numpy.random. And one trick that we always ask you to do is whenever you have random values, obviously every time you run it, you'll get a different answer. But when we want to grade that, or we want the auto-grader to grade that, or if you have a project and you want to publish it and to other people, you need your result to be reproducible. So for that, we want to still do a random thing, but we want that random to be the same every time we do it. So again, these are random numbers. They don't follow any pattern, but every time I do it, I want it to be the same thing. So what I do is I just use this random.seed. There, you can assign some values to it. I'm not exactly sure what each value means. So all you need to know is that if you set this to different values, you will get, again, different random matrices, but they will be the same every time you run them. So hopefully if you run it, you will get the same answer as me. Just remember in some cases, in some laptops, in some OSs, sometimes these numbers are different. So like the C10 is not essentially equivalent to this. And finally, if you want to store them in a variable, you can easily do that. So you can just put them in a variable. The thing is that it's by default, it's saved as a NumPy array. So sometimes you, especially later in the course when we also have PyTorch, sometimes you get some issues of, oh, I have a PyTorch kind of tensor, which is on GPU, and I'm trying to multiply it in a NumPy array, which is in CPU, and I cannot do that. So just be careful. Like you can use this function called type, that's also another golden thing for debugging, to kind of show you that what each value or what each variable is from the lens of Python. So here, for example, this random matrix variable is just a NumPy array. So really use these two a lot in your debugging, the type function and the shape function, because that they will really help you to see what's going on. So just as a practice, you can also follow it with me. So you can set the random seed to 10 and then try to define these kind of matrices. So try to define A, B, and C. There are 3 different random values. And let's see how do they look like. So first of all, they should be the same. And they are the same. So the first thing that you test is if your seeding is actually working. So you generate 3 different matrices, same size, and you get the same values. So now just out of curiosity, let's see what's going to happen if I set this to a 4x4 matrix. Okay, so yeah, I'll get an error, obviously. It's just for curiosity. We want to see. Print C. So you see, now A and C are different from each other, and all the values that you have are also different from each other. So just remember that they don't necessarily generate the exact same number. As long as your objects have the same shape, they will be the same thing. But as soon as you kind of change them, they will change. So let's just go back. Okay, now let's see some properties of matrix multiplication. So the first property is what we call association property. So essentially, the idea is that, does it matter if I multiply, like let's say I have 3 ABC matrices. Does it matter if I start from AB and then multiply it in C, or I start from BC and then multiply A in them? And the answer is no. As long as you do the same order of operation, it's good. The problem is you cannot do, let's say, A times C and then multiply it in B. Because first of all, in this case, yes, all the matrices are square, so you won't get an issue with the dimension. But let's say you had a case like this. So you had a case where your A matrix is 3x4, your B matrix is 4x8, and your C matrix is 8x22. You cannot even multiply A and C because the dimensions do not match with each other, okay? So remember that matrix multiplication is associative, so you can start from any order that you want as long as you're following the sequence. And you can kind of check to see if they're equal to each other or not. And finally, we have also another important thing called the distributive property of matrix multiplication. And it just tells you that, hey, in numbers, we have this kind of thing that you have 2 times parentheses, for example, 3 plus 4, you can easily find it. So this is 7 times 3 is 14. That's one way to find it. Another way is you multiply 2 and 3 to get 6, and then you multiply 2 and 4 to get 8, and then you get to 14. You can also have the same thing for matrices. So if you have something like A times B and C, in this case, it also behaves like numbers. So you can really multiply A with B and then add it to A and C. But that's almost about it. So without making any further assumption, you cannot really use any other intuition that you have from numbers in matrices. So just remember that, because again, that's also something that a lot of the students make mistake with. They assume that, oh, this looks like a number, so I can solve it. And another thing that I want to mention, you will definitely see that, and you will definitely ask yourself, why is it like this? Is that, let's see a case where X is a vector and is n by 1. A is a matrix that is n by n. Now, can you tell me what is X transpose? Should be 1 by n, right? So now let's do this multiplication. X transpose A X. So what is the dimension here? I just write the dimensions below them. So it's 1 by n. This is n by n. This is n by 1. And as we said, it doesn't matter where do I start. Let's say I start here. X transpose A is going to be 1 by n. And then multiplied by X is going to give me a 1 by 1 matrix or a scalar. So anytime you saw anything like this, like X transpose AX, or I don't know, Y transpose AX, a vector transpose times a square matrix times something else, something else which is a vector, you always get a scalar. It's always a number. And if you remember from the probability slides, you had such term like X minus mu transpose times sigma inverse times X minus mu. And that whole giant thing will just reduce to a number. And it gets even more fun because you see the transpose of a scalar is itself, right? Do you agree? It's just a 1-by-1 matrix. So now the funny thing is that Y transpose AX transpose should be equal to Y transpose AX. And if you want to transpose something like this is how it works. You always start from the last element and you go back for it and do the transpose. So it's going to be X transpose A transpose Y. Transpose of a transpose is itself. So you get to something like this. So in some part of the course, we will find some proof that's, oh, we got to something like this, like Y transpose AX, and then we replace it with X transpose A transpose Y. And you'll be wondering what happened here, and this is what happened. So two things to remember. Anything in this form, we call it the quadratic form if the x's are equal to each other. Like basically, we have X transpose AX instead of Y transpose AX. We call this the quadratic form. It essentially acts like a polynomial in numbers, and it's going to be a scalar, okay? And if this value is positive, regardless of what is x, so if x is a zero vector, is a vector of like -1, -1s, minus millions, it's always positive. We call A to be positive semi-definite. If it's positive or zero, it's positive semi-definite. If it's always greater than zero, it's just positive definite. So if you heard about this thing, this is basically the kind of definition, the formal definition. Any questions on this? Okay, good. So let's continue with another important definition, which is called the rank of a matrix. So the way we see matrices is we think each matrix represents some sort of a transformation. So there are two ways to see matrices. One of them is that they are representing some sort of a geometric transformation, such as, for example, rotation. Or we can also see it as, oh, they are basically the coefficients of an equation. These are really the two areas that you see matrices a lot when solving an equation or in the geometric sense. So in both cases, we have a very important concept called rank, which tells us a lot about how this matrix will look like. So sometimes we have matrices like this, like you see, you have a 2, 3, 4, 6. At the first glance, there is nothing wrong with this matrix. It's just like any other matrix that we have. But this matrix has a special property. So if you look at the columns, you see we have a column of 2 and 4, and then we have another column 3 and 6. The idea here is that I can write the second column as some sort of a transformation, a linear transformation of the first column. How can I do that? So again, let me just draw it on the board. So I have 2, 4, 3, 6 here. Let's call this one V1. Let's call this one V2. Okay, this is the first column. This is the second column. The second column is just essentially equal to 3/2 times the first column. And you can check that really. Just multiply this by 1/2. And you'll get 3 and 6. So in this case, whenever we have such relationship between the matrices, or it could also be like, for example, V2 plus V1, we have a new, for example, column. Whenever you have a linear relationship between the columns of your matrix, or even between the rows of your matrix, essentially what we say is that this matrix is not a full rank matrix. So what does that mean? It essentially means, if you think about this matrix, you can think about each column as representing some sort of an information, okay? So it can be, for example, a geometric direction, or it can be being, for example, the coefficients of an equation. So we just call all of them a bunch of information. Essentially, what this tells you is that the two columns that you're having, they have redundant information. So if you really think about these two columns as both of them are representing a geometric, like, for example, direction. So this is 2, 4, and this is 3, 6. So this is your first column, and this thing right here is your second column. As you can see, they are representing the same information. They're just pointing towards the same direction, okay? So in this case, we are saying that, okay, this matrix, it has some redundant information. If you look at this matrix, you're not going to get two different directions because you have two different columns. We'll get just one direction. In terms of the equation, it's probably easier for you to understand. So just a quick overview of basic math. So if you have 10 equations and 10 unknown variables, and if the 10 equations are independent, you'll get a unique solution, right? But if you have, let's say, 8 variables and you have 10 independent equations, what's going to happen is you will have some, like, kind of some contradiction at some point, because you cannot really satisfy all 10 equations with just 8 variables. So essentially, your system of equation has no answer. So here is the idea. If I have a very simple equation like this, x plus y is equal to 2, x plus 2y. So the answer is x equal to 1, y equal to 1, right? We all agree on that? So the thing is, if I create a new equation as 2x plus 3y equal to 5, I don't have 3 equations, because the last equation is a fake equation. I just built it by adding these two with each other, right? So again, 1 and 1 satisfy this equation. If you look at it at the first glance, if you didn't know how I built this, you might tell me that, hey, you have 3 equations, 2 unknowns. So it's impossible for you to find a unique answer here. But I found an answer. And the reason for it is because one of these equations is fake. The other way that I could do this, also I can multiply this by any number. I can have 10x plus 10y equal to 20. I can have 20x plus 20y equal to, I don't know, 40.